Hello and welcome to Chapter 8. We're going to be talking about probably the most important concepts of the entire semester in this lecture. It's going to be a bit longer. My apologies. It's really important to know these concepts and the steps that we're going to take to actually conduct hypothesis testing. So brew yourself a nice cup of tea or get your favorite beverage and salty snack, and let's get ready to learn. First, a little bit of review. I think that sleep makes you happier. I measure how many hours of sleep you had and then measure your happiness using a 1 to 10 scale. What kind of variables are we measuring here? We're measuring two numeric variables. That's going to be A, two numeric variables, because hours of sleep is hours of sleep. And then a 1 to 10 scale, even though that's an interval scale, it's still going to be numeric. All right, so what are we up to today? We are talking about hypothesis testing. So the first thing you have to do when you are going to test hypotheses about populations, because we're always interested in populations, not necessarily just our sample, what you first have to do is establish a particular distribution for your null hypothesis. Okay, well, what does that mean? We'll get there in a second. Then you calculate your sample test statistic. We're actually going to be doing kind of real statistics, not that we haven't been doing that, but instead of descriptive statistics, we're doing inferential test statistics. And then we're going to see how likely that calculated test statistic would be if there really was no effect of something that you're looking at. In other words, the null is actually true. The null hypothesis is actually true. All right, so let's break that down with an example. So if I think that wearing glasses causes people to become smarter, what I would have to do in terms to test that in terms of hypothesis testing, I would first set up a distribution of smartness for people who do not wear glasses. And so this is saying, hey, I want to figure out, well, what's the smartness of people who don't wear glasses? That's the null hypothesis, because that's saying that, well, really there isn't any type of effect of wearing glasses on smartness. And so I want to first establish, here's a distribution of people who don't wear glasses and look at all of their smartness, okay? But then I'm going to take a group of people who do wear glasses, and I'm going to get the average smartness of that group, okay? And I'm going to compare that average smartness of the group of people who does have glasses. I'm going to compare that to the distribution of smartness of people who don't wear glasses, right? And I'm going to ask the question, well, is the smartness, the average smartness of people who wear glasses, is it way higher than the average smartness of people who don't wear glasses? And is it so much different or so much higher that it's actually really unlikely that I would see such a high smartness for people if in fact there was no effect of wearing glasses on smartness. Okay, so again, let's break that down a little bit more. We're wondering if wearing glasses causes smartness, and how we have to approach that is to basically assume first that glasses don't cause smartness, but then I'm going to try to disprove that null hypothesis by saying, well, if I find a group of people who wear glasses and they happen to be a lot smarter, well, then that's going to be very different from the people who are not wearing glasses, and therefore it's unlikely we would see such a high smartness if in fact there were no effect. So there probably is an effect of wearing glasses if I see a very high smartness average for the people who wear glasses. Okay, we'll walk through some examples of that later on. Now in psychology, we're often interested in comparing the mean of a sample to, let's say, a population distribution or the mean of two different samples to each other. You know, if you have an experiment and you have an experimental condition where you actually give somebody a drug or give them an intervention of some kind, and then you have a control group that doesn't get that drug, doesn't get that intervention. Then you want to compare some kind of outcome between those. That would be comparing the average of one group to the average of the other group. So we do this all the time in psychology. That's why we're going to talk mostly today about means, about averages in terms of hypothesis testing. But as you'll see in the next couple of chapters, that's not the only kind of test statistics that we can compare or talk about when we're talking about hypothesis testing. And in order to talk about hypothesis testing, we kind of need to talk about something called the distribution of sample means. We've talked about different kinds of distributions so far. Mostly we're talking about frequency distributions, just distributions of different people's raw scores, right? We've also talked about Z distributions, and we've talked about the standard normal distribution, which is made up of basically infinite amounts of Z values, okay? Well, here's a different distribution, and it is called the distribution of sample means. And it's a bit hard to wrap your head around this one, but let's give it a shot, and definitely reach out if you have any questions or if you want to learn more about it. So the distribution of sample means is another kind of theoretical distribution. It's not a real distribution, but it's a theoretical distribution, sort of like the standard normal curve. Okay. This is a distribution made of a bunch of different means from a bunch of different samples for whatever you're measuring. So if you're measuring anxiety, you gather, let's say, 1,000 different samples of 50 people, and you average in each of those samples of 50 people, you average their anxiety on a scale of 1 to 10. This is now a distribution of a bunch of averages, of a bunch of means of samples. Okay, so it's another cognitive leap here. It's not just raw scores. This distribution is actually made up of a bunch of sample means. Okay, so the actual definition is the distribution of all possible sample means for all possible samples of a particular size from a population. Okay, now this distribution is going to be what's called a comparison distribution. It's going to correspond to the null hypothesis. So that's the hypothesis that there really isn't any effect of one variable on another variable. So for instance, in that, this would be a bunch of sample means of smartness or intelligence for people who do not wear glasses, okay? So I have what's called a comparison distribution, and this is the distribution of sample means from a bunch of different samples of people that I've taken that don't wear glasses, and I've taken their average intelligence, basically their smartness. Now, once I establish this distribution, what I'm then going to do is go find a group of people that is wearing glasses, and I'm going to get the mean intelligence or mean smartness, the average smartness of that group, and I'm going to compare it. And I'm going to ask, where does that number, the intelligence, the average intelligence of people with glasses, where does it fall on this distribution? Because if it falls way, way high to the right, that would be very unlikely. Or if it falls way, way, way to the left, if people are actually less intelligent who wear glasses, that would also be very unlikely. And so we could say that if, in fact, people who wear glasses do fall way, way, way on the extremes of this distribution, then they probably don't actually belong to this distribution, which means their smartness is different than smartness of people who do not wear glasses. Okay, hopefully that makes sense. We're going to go through a bunch of examples of that later on, but let me know if you have any questions. So why do we have to use the distribution of sample means? Well, what we've been doing up to this point is actually looking at raw scores and converting them into z-scores, and then saying, where does that individual person's score for some variable fall within the standard normal distribution, and how likely or unlikely is it that we would see such an extreme score or higher, or such a score or lower, right? That's for individual scores. Well, now we're interested in going beyond individuals because we're talking now about samples and trying to figure out if our sample somehow represents a population. We're trying to say something about the population based on our sample, okay? And how we do that as scientists, as psychologists, is we gather samples, and usually we're going to be computing some kind of average or mean of a variable that we're interested in. You know, average reading speed, average comprehension, average memory, average anxiety, or whatever it is, right? And then we're going to compare that average to, we can't compare it to just other individual scores. We have to compare it to other averages. And so that's why we need a distribution now, not of just individual scores or z-scores, but it's a distribution of sample means. So we can compare our sample mean to kind of a hypothetical distribution of sample means. So let's talk more about how we would actually go about theoretically constructing the distribution of sample means, while also knowing in the back of our minds that we don't actually go out and collect like hundreds and hundreds of different samples. That would take way too long. We usually just collect one sample, and then we compare it to this theoretical distribution of sample means, which we can actually create mostly using statistical software. Okay, so this isn't, again, this isn't like a real distribution. We're not going to go out and collect hundreds of samples and calculate the sample means for all those samples, but we do need to construct this distribution of sample means, at least in a theoretical way, using computations. So let's see a little bit more about, well, how would you go about trying to build such a distribution out? So in science, in any field of science, it's important to conduct multiple studies to test different samples from a particular population of interest, okay? So you don't want to just rely on one single study's data, because every single study is going to get a slightly different sample, or sometimes a majorly different sample. And naturally, the variable of interest, that whatever you're interested in, is going to have a different mean, a different average from all of the people in your sample between different types of samples, right? And so I might collect information on college students in this research methods class, and then that'll give me a particular average for a particular score. Maybe I'm interested in your GPAs. Well, then next semester, I'm going to do the same thing. I'm going to collect data on the next semester's worth of students and average all of their GPAs. And those GPAs, the average of those GPAs will be different from this semester's, right? And so it's important that you don't just trust the observations and the results from one single study, because every time you collect data, you're going to end up with slightly different results, or maybe majorly different results, right? And so you can see that we talked about this a little bit last chapter. Sample one, you're getting different people in the population, and so naturally they're going to give you a slightly different average from sample two, right? So we don't actually prove anything about a behavior or a variable of interest from a single study. So I'm going to try to show you why it's important that we conduct several different studies, meaning collecting several different samples from the same population when we're testing a variable of interest. So let's assume that we have an overall population of young adults, okay? And we're interested in the number of hours they spend on social media per day. All right, so let's imagine that we have this frequency distribution, which is a normal symmetrical distribution, although that might not be how it actually is in the true population. This is just an example. So we've got a distribution with a mean, which is represented by that little mu, that Greek letter mu symbol. We can't ever know what the true population mean of hours people spend on social media is per day, because we can't measure the entire population, right? But as researchers, we're interested in taking a sample from this overall population, and we are taking, in this instance, 15 different people, and they're telling us how many hours they spend on social media per day. We're taking 15 different people, which is represented by those 15 different arrows, from the overall population to create our first sample. And let's say if we were to take all the individual scores on number of hours they spend on social media per day and we put them into a frequency table, let's imagine it's also normally distributed, meaning, and symmetrically distributed, meaning that there's only a few people who spend very low amounts of time on social media. There's only very few people who spend a lot of hours on social media per day, and there's a lot of people, represented by those taller bars in the middle, who spend kind of a middle ground number of hours on social media per day. And let's say the average, represented in this case by X bar. So you can see that the mu symbol, which is that little U with a teardrop on it or an extra bit on it, mu is how we represent population means. X bar is how we represent sample means. So the sample mean for this particular sample of, let's say, 15 people was 2.3 hours per day on social media. So that's our first sample. That's our average number of hours per day on social media. Well, that's cool, but let's imagine that we take another 15 people from the original population and we find that in those people, so sample number 2, although it's similar distribution, we've got a lot of people who spend kind of an average amount or middle amount of hours on social media per day, and not that many people at the tail ends, meaning very little or tons of hours on social media per day. The new average, which is represented again by that red up and down line, is going to be 3.1 hours. Well, that's interesting because we just said that sample 1, the average was 2.3 hours, and now it's 3.1 hours. So which of these is closest to the true population mean? Well, we can't really know that. But something interesting happens if we keep on taking samples out of this population, more and more samples, we're getting different types of average hours of social media per day from these different samples. But something interesting starts to happen when we take a lot of different samples. So here's this metacognitive leap we have to take together. And basically what's happening is, well, what if we took the sample means, meaning the average hours that that people in that sample spent on social media, and we plot those on a distribution, a frequency distribution chart. What would happen? Well, what would happen is we no longer have on the x-axis just numbers of hours that people spent on social media. Now we have average hours of social media from each of those samples. And if we kept on drawing tens, hundreds, thousands of samples from that overall population, and we plotted each of the sample means, what would eventually happen? What would eventually happen is now we have a distribution of sample means, which is the lower graph, and the interesting thing here is that the mean of means, if you will, the distribution of sample means, the mean of that distribution, which is the mean of all means of all samples, that's kind of tricky, right, is going to be the same as the original distribution from where all those samples came from. Meaning we'll have finally found out what the population mean, the true population mean of hours people spend on average on social media is. So that's kind of interesting. And we'll talk a lot more about that when we get to hypothesis testing, because this is the basis of hypothesis testing. But for now, it's you should know, okay, we should be taking more than one sample from a population because it might be inaccurate to just see the mean from one specific sample. And if we take a bunch of samples and study a bunch of different people from the population, then if we plot those, we're more likely to get kind of at this true population mean. And I know I ran through that a little quickly, and if you want a super good video to wrap your head around the idea of the distribution of sample means, definitely check out Khan Academy. This link is awesome. So just again, kind of rounding this out, right? The distribution of sample means is a distribution of all possible sample means for all possible samples of a particular size from a population. So we were taking sample sizes of 15, but you could take sample sizes of whatever. This is a distribution of all of the possible sample means, okay? And then you can see that now the x-axis becomes the sample mean value for whatever your your variable of interest is. If it's normally distributed, which it will be, and you can see that why that is on the Khan Academy video, the actual population mean will be in the center, and that will be the same as whatever the distribution mean is that the population originally came from. And then you will have kind of this nice normal distribution, and on the tail ends are extreme types of sample means, but most sample means kind of bunch up in the middle, which is why that peak is higher. And again, why that's important is because we don't want to rely on results from just a single study. That doesn't really prove anything, although it might help us get an idea of how some behavior works or some cognitive process works. So because one sample might be closer in terms of its sample mean to the true population mean than other samples, we can't really rely on just results from one. And so we want to imagine there are thousands of these different samples that we ultimately take and place on a distribution of sample means, and then we're going to use inferential statistics which will rely on this distribution of sample means to say, well, how likely is it that for any sample mean that we get, how likely is that given all possible sample means? Okay, and you'll see what I mean when we get there. Now, we run into a little bit of a problem in hypothesis testing, which is that we still need to have some assumptions of normality, meaning distributions have to be normally distributed in order for us to look up in tables what is the probability that I would see this mean or greater, or what is the probability I would see this raw score or lower, what is the probability I would see this z-score or higher, right? Those kinds of things. Well, in order to use those tables, we have to have normally distributed data. And so this becomes a little bit of an issue because it's like, well, what if the original population isn't normally distributed? What if I'm sampling from a population that is not normally distributed for whatever variable I'm interested in? How is that going to affect the distribution of means? And then does that mean we are unable to use those tables that we've been using so far? Well, there's this cool idea in statistics called the central limit theorem. And basically what it states is that when you have a population, no matter what the shape of the distribution of that population is, remember this could be social media usage per person in a large population, it could be heights, it could be IQs, it could be happiness, it could be whatever. Those things aren't always normally distributed. Sometimes they'll have a really skewed distribution. Well, money is like that. Very few people have a ton of money, whereas a lot of people have kind of like a moderate amount of money, right? And so that would be a very skewed distribution. But what happens is if you keep taking samples from a population, even if it's not normally distributed, what happens is that the distribution of means becomes normally distributed as sample sizes tend to increase. And so once you get a sample size of 30 or above, and you keep on taking samples of 30 or above, keep on taking more samples and more samples and more samples, and creating this distribution of means, the distribution of means will always be normally distributed, even if the original population distribution wasn't. So that's pretty cool. And that helps us because we need the distribution of means to be normally distributed, in order for our hypothesis testing logic to work out. And we'll talk about that in a second. So what this picture is showing you is that the population, which could be normal, it could be uniform, it could be skewed, it could be anything, it could be random. If we take a bunch of samples of sample size 10, n equals 10, that's kind of the middle row there, you can see that the distribution of sample means, or the distribution of means, using many samples of, of size 10 will start to become more normal looking. They'll start to become a little bit more symmetrical. They'll start to become looking a little bit more normally distributed with, lows at each end and then a high peak towards the middle. And then instead of, if we were going to take sample sizes of 30 or more, and so this is sample size of 30, n equals 30, you can see that no matter what the original population distribution was, now we have a normally distributed distribution of means, and that is what we want. So in statistics, there are usually like 3 different distributions we're talking about. There's the original population distribution. We don't usually know what that actually looks like because we don't typically get to measure entire populations worth of people for anything. But it doesn't really matter what the original population distribution looks like for a particular variable we're interested in, as long as either it's the original population distribution is normal, or it doesn't have to be normal as long as we take sample sizes of at least n equals 30 from the original population distribution. Because we don't really care what the original population distribution is. It's nice if it's normally distributed, but what we do definitely care about is if the distribution of means is normally distributed. And once we get down to the distribution of means, we have this nice distribution which we're going to compare then our sample. And so you can see that on the very bottom of this is just this little kind of scraggly sample. It looks like there's 64 people in that sample, and that sample isn't necessarily normally distributed, but we're going to compare the mean of that sample to the distribution of means. And you'll see what I'm talking about a little bit more. One thing that I want to note though about this is, what do you think, or what do you see happens to the variability, the measure of spread, which in this case would be standard deviation? What happens to how spread apart all the data points are when we go from the original population down to the distribution of means? You can see that the distribution of means is much more tightly packed around the mean. And that's because no matter how many people you sample from an original population, their scores tend to kind of average each other out. So there's actually like much less variability in a distribution of means, meaning the standard deviation is lower than the original population it came from. They have the same mean. They have the same mean, the original population mean and the distribution of means, they have the same mean, and you can see that. It looks like the test scores are 200 for whatever variable they're interested in. And the mean, and that's where the mean is, the test score of 200. And if you convert that to z-scores, it's 0 for both of them. So this is kind of, this is a cool thing that we need to think about, is that okay, the distribution of means has lower variability, but the same mean as the original population from which it came from. So I want to talk a little bit more about why variation in the distribution of means is less, the spread is less than the original population distribution. We have to introduce a concept called the standard error. And the standard error is basically the standard deviation of a distribution of sample means. But it's not exactly the same thing as the standard deviation of the overall population that this distribution of sample means is coming from. And you can see that represented by this formula over here. So the standard error, which again is the standard deviation of the distribution of sample means, the standard error is represented by sigma, lowercase sigma, and then as a subscript, x bar. And that x bar we know is the mean, and this is saying the standard deviation of the distribution of means. So it's a little different from the original population distribution, which is in the numerator on the other side of the equal sign. That's just sigma by itself. That's the original population standard deviation. And so what you can see here is that because we take a sample of some sample size, n, we're taking people from this population, our standard error, which again is like the measure of spread in the distribution of sample means, is going to be less than the original population because the standard deviation and the amount of spread depends on how many people we grab. The more people you grab in a sample, the more representative it is of the overall population, but also the more precise the values are that you're getting for a sample mean. And so if we have a really high sample size, a very large n, and you can see, just based on basic algebra, if you have a really high number in the denominator, well, what happens to the overall number that you get out? If you have a really high number in the denominator, you get a really low number overall. And so what the saying is, this equation is showing you is that as sample size increases, the standard error decreases. So we actually have less variability in the distribution of sample means compared to the overall population distribution. Hopefully that makes sense. So standard error is the standard deviation of a distribution of sample means. But what does that actually mean? It is a representation of how much we expect the sample mean to differ from the actual population mean. Because obviously whenever you grab a sample from a population, the mean of whatever variable you're going to be measuring, it's not going to be identical to the true population mean. That's just because of a random sampling error, right? Like you just happen to get a few people who have slightly higher anxiety in your sample compared to the true population average anxiety, for instance, or something like that. Okay, so to summarize this central limit theorem, it's saying that the mean of the distribution of means is the same as the mean of the original population, but the spread of the distribution of means is going to be less than the spread of the original population distribution. And the shape of the distribution of the means is approximately normal if either the original population was normally distributed for whatever variable you're interested in, or the sample sizes that make up the averages, the means of the distribution of means, the sample sizes are at least 30 people or more. And that number is based on a lot of modeling and things that mathematicians have figured out over the years. So definitely want to memorize that number. You don't need to know exactly like why 30 is the most important thing. As long as it's sample sizes of 30 or more, and usually we are grabbing sample sizes of hundreds of people, and sometimes thousands of people, then all of the things we're going to talk about for hypothesis testing apply. We can assume that normality has not been violated, and we can actually try to use things like unit normal tables to figure out percentages and probabilities and things we'll talk about in a second. And like I just said, it's important because it doesn't eventually matter what the shape of the original population distribution was, as long as we can get a sample size that's above 30, we're good for these next few steps that we're going to talk about in terms of hypothesis testing. So let's revisit this figure because it actually speaks to hypothesis testing, even though I didn't really talk about that a minute ago. What the idea in hypothesis testing is you're trying to see if your experimental group has a different mean of whatever variable you're interested in than your control group. Or you can try to say there's some kind of an effect of like drug X on a population when you can compare it to people who were given a placebo. Or you can just try to see if like the average test scores of your class are the same or different as the average test scores of previous classes. So there's a lot of different ways we can think about hypothesis testing, but what it really comes down to is we find a distribution of means, and then we compare a sample, one sample that we've got from whatever population we're interested in. We compare the sample mean to that distribution of means and try to decide whether or not it's a really, really, really extreme and unlikely sample mean. And we'll talk more about that in a second. But you can see on this figure that the sample that they've got, which is the very little bottom portion denoted by C, they've got a mean test score of 220. Okay, now if you were to place that mean of 220 on the distribution of means, which is what it's trying to indicate where that arrow is pointing to on the sample or the distribution of means, you would see that that sample mean of 220 is very extreme. It's a really high sample mean compared to the entire distribution of means. It's in that little tiny tail on the right side. And you can see based on the z-scores that it's above 2 standard deviations above the mean for that distribution of means. The original, the mean of the distribution of means is 200. So 220 is quite high. And what we want to do is say whether that mean, that sample mean of 220, is that likely given the original, given the distribution of means, or is it unlikely? And then we can make some decisions about these populations and our hypotheses. So remember, what we're trying to do here is we're trying to find our sample mean, and we're trying to locate that sample mean within the distribution of sample means. All right, this theoretical distribution of sample means for the population if the null hypothesis were true, right? The distribution of sample means if the null hypothesis was true. And we look at where does our sample mean fall in this distribution of sample means. And if it is on the extremes, okay, if it's an unlikely, improbable score because it's very high or it's very low, and so it's on one of the edges, right or left, of the distribution of sample means, if we find that to be the case, then it indicates that our sample mean is, first of all, very different from the mean of the distribution of sample means, which again is the same as the population mean. So it means that the sample mean is really, really different from the population mean for that variable. And therefore, we can probably conclude that our sample mean doesn't even belong on that distribution. It's somehow, we're talking about two different groups of people entirely. And therefore, we can say that the null hypothesis is probably not the case. There probably really is an effect happening here because we found such an extreme score that it probably indicates that there is something going on compared to the null hypothesis. As an example of this, let's say we have taken hundreds and hundreds of samples of university students from across the United States, from different universities, okay? And we've taken, let's say, sample sizes of 100 from many, 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 many different universities across the US. And we've computed an average GPA for each of those sets of 100 students, each of those samples of 100 students from each of those universities. And that's what you're seeing in the blue distribution. Okay, this is now the distribution of sample means for all of those mean GPAs that we've calculated. All right. But now what we want to do, so that sets up kind of our comparison distribution, right? That's kind of the null hypothesis here, is that CU psychology students have the same or have no difference in average GPA. But we're going to test an alternative hypothesis that CU psychology students actually have a higher GPA than other university students. So what you see here in the green, that is our sample, just one single sample of CU psychology students' GPAs. Okay, so that each of those bars would be a frequency of how many different students got the corresponding GPA. All right, but then we're going to compute an average, which is going to be right in the middle, as you can see, because the green distribution is a symmetrical distribution, so the mean's in the middle, and we want to know, okay, is this sample mean of CU psychology students, is this average GPA of CU psychology students, is that different? Is that extreme compared to the distribution of sample means that we already had? Okay, and if it is extreme, then it's unlikely that CU psychology students' GPAs actually lie on the same distribution, meaning CU psychology students are somehow different in terms of their GPA than the rest of university students across the US. Well, it looks like, at least visually, the mean GPA for CU psychology students is quite a bit far to the right of this distribution, of the blue distribution, right? It's quite far to the right, meaning it's an extreme value. It's a bit of an outlier, and it would be improbable, unlikely that we would see such a high average GPA if in fact CU psychology students were just like all other university students. So if the null hypothesis was true, that there's no difference in average GPA between CU students, CU psychology students, and other students, then it would be very unlikely that we'd see such a high GPA for CU psychology students. So more than likely, it means that these are two different distributions, and we would reject the null hypothesis that in fact these two groups, CU psychology students and everyone else, has the same GPA. Okay, probably CU psychology students are just somehow qualitatively different. I know that was a long lecture, my apologies, but this is a very, very important concept. We're trying to establish a distribution that corresponds to the null hypothesis, and then we're trying to say, okay, but is our sample aligned with that, or is it different? Because if it's very different, we can probably reject that null hypothesis. And we're going to talk more about null and alternative hypotheses and how we actually go about hypothesis testing in the next video. I'll see you then.